Okay, I'm going to go fairly quickly through this. There are six basic graphs that I hope you know already. If not, please commit these to memory. From grade 10, y equals mx plus b, which is a linear graph. From grade 11 math, I hope that you know y equals x squared, which is also known as a quadratic. And last year, I believe you spent a little bit of time changing that quadratic and doing some of these transformations to it. If you don't know the quadratic, it goes through 0, 0, and over 1 and up 1, over 2 and up 4, over 3 and up 9, and same on this side, 1, 4, and 9. Third graph, y equals the square root of x, and that looks a little bit like a sideways quadratic, and so it goes over 1 and up 1, over 4 and up 2, over 9 and up 3, and to the side. The absolute value graph goes through 0, 0, over 1 up 1, over 2 up 2, over 3 up 3, and it looks kind of like a V function, does that in both directions. The cubic graph through 0, 0, 1, 1, and negative 1, negative 1, 2, 8, negative 2, negative 8. And it looks a little bit like this. Let's go to the next one. Y equals 1 over x is known as the reciprocal graph. This one's a little bit trickier. On this side and on this side, you get a graph, and it gets closer and closer to 0 as the x's get bigger and smaller, and as it gets closer and closer to x equals 0, the y values get bigger and smaller in each of those directions. It goes through 1, 1, and negative 1, negative 1. It also goes through 2, 1/2, 3, 1/3, 4, 1/4, etc., etc. Once you have these graphs committed to memory, then we can move on to the next part of this, which is how do we move them and shift them around? So the first type of movement that we'll do is a shift. The technical name for that is a translation. So let's take a look at that next. Okay, in a translation, the graph is shifted in the x or y direction, but the shape stays the same. So a shift in the x direction means you're shifting the graph left or right, and a shift in the y direction means you're shifting the graph up or down, but the shape always stays the same. That's really important, and in mathematics, the same is also known as congruent. Let's take a look at vertical translations. So those are the ones that shift up and down. If you start off with y equals f of x and you add an a value, it shifts the graph up, and it shifts it up a units. If you have your same function, but the a value is negative, then it shifts the graph down a units. So let's take a look at an example of this. If you start with y equals the square root of x, and the graph looks like this, and we explore what the function y equals the square root of x plus 1 looks like, well, that plus 1 is a shift up 1. So the entire green graph gets moved up 1, and therefore looks like this. And you can quite easily find points. For instance, 1, 1 was a point, now 1, 2 is a point. So the entire set of points that you could easily graph on y equals root x is quite easy to find on y equals the square root of x shifted up 1 plus 1. The same thing works horizontally, the same sort of idea. So if you change the x value to x plus a or the x value to x minus a, it shifts the graph horizontally, which is left and right. So the rule is that when x becomes x plus a, it actually shifts it left. So this is opposite to what was happening before, and x minus a shifts it to the right. So an example looks like this. If you have the square root function, which originally looks like that V shape, so it goes through 0, 0 and up 1 over 1, up 1 over 1 in both directions, and then you ask, well, what does the function if I take the whole graph and make it absolute value x plus 4. Well, the plus 4 works like the plus a, and it actually shifts the whole graph to the left. So you end up getting a new graph that looks like the v is now over here at negative 4, and it goes over 1 and up 1 from there. So everything moves left 4. The incredible thing about this is it works for all functions. It doesn't matter whether or not we know the equations. Okay, here's another example. We've got a point 3, negative 1, and it's on the function y equals f of x. What is a coordinate or a point that has to be on the function y equals f of x minus 2 plus 5? So if you take a second to dissect this, this means that the whole graph has gone right 2, and this means that the whole graph has gone up 5. So that means the point 3, negative 1 has gone right 2. That would take it to 5 in the x direction, and up 5 means that the negative 1 would now move up to positive 4. So therefore 5, 4 must be on that graph. A second type of transformation is a reflection. And reflections flip a graph over an axis. The two main kinds are a reflection over the x-axis. That takes your original graph to y equals negative f of x. So if you've got some graph up here, that's a function, the new one gets reflected over the x-axis, and so I didn't do a great job, but all of the values become negative. If they were negative, if that was your original function, then all of the values become positive. Essentially, they have to be the same distance away at any point from the x-axis. Similarly, there's a reflection over the y-axis. And a reflection of the y-axis takes y equals f of x, so if you've got, say, a square root function, to y equals f of negative x. And so what's happening is, this is the y-axis, in green here, all of the values are now reflected across that y-axis. So the x values, if they were positive, become negative, and if they were negative, they become positive. And again, we don't need equations to be able to do these. We can do them with points, and I'll do an example of that in a second, or any function at all, as I did with the reflection over the x-axis. I didn't have an equation for that. That doesn't matter. Here's that example with a point. 4, 2 is on our original function. What must be a point on this y equals negative f of negative x? And essentially this is just a double reflection. So 1, 2, 3, 4, 2 was on our original f of x function. When I apply the reflection over the x-axis, it would be here, and then a reflection over the y-axis would be here. And if I did it in the opposite order, and I reflected it over the y-axis first, and then the x-axis, either way would still give me the same answer of negative 4, negative 2. So notice that the order of reflections, multiple reflections, doesn't matter. And order is going to matter in the future, but multiple reflections doesn't matter. You might want to add that into your own set of notes before continuing to the last section on compressions and expansions. Okay, good. Hopefully you're writing all these extra little notes in and asking yourself what-if questions to help us get a deeper understanding of this. Here's the last section. There's another type of transformation that can happen, which is known as a compression or an expansion. And these change the shape of the original graph. And there are two types of compressions and expansions. The first one we'll take a look at is what happens if we do a compression or expansion vertically. And so vertically, again, is up and down. So if you start with a function and you add a multiplication value in front of it, I'll call that value a. If a is bigger than 1, something happens. And if a is a basically a fraction between 0 and 1. I guess it could be a decimal. Something else happens. And here are those two things. If the a value is bigger than 1, and this happened, if you remember back to last year with quadratics, if you had a value in front of x squared, it multiplied all of the y values by that number. And if you had a fraction in front, like 1/2, it compressed all of those values. And you could say it compressed them by a factor of 1 over a. I guess technically it's more like a compression of a still, because you'd say that it's a compression of 1/2. The English language is a bit weird with that. So let's take a quick look at an example of that. If you start with the graph of y equals x cubed, and so I know a few points that it goes through, that's 2, and I'll just say that's 8 up, and -2, and that'll be -8 down there. The graph looks sort of like this. If I want to know what y equals 1/2 x cubed, that takes all of these values and the y values and cuts them in half. So where this was -8, it'll now be at -4. Where this was -1, it'll be now -1/2. And so my new graph looks similar, but compressed towards the x-axis. And you can, and this is important, you can quite easily find points to graph it fairly accurately without having to use your graphing calculator or make a table of values, just by knowing, back to the beginning of this whole lesson, just by knowing what these basic graphs look like. And the last type is a horizontal expansion or compression. So if you start with y equals f of, and now we in the horizontal are going to affect the x value, so if you multiply it by an a, again, there's a couple different things. If a is bigger than 1, or if a is between 0 and 1, these things happen. If the a value is bigger than 1, you actually are compressing the graph. In this case, you're compressing it by a factor of 1 over a. If it's between 0 and 1, you're actually expanding your graph horizontally, which means your graph is getting wider. This one is getting less wide. Towards the y-axis, it's compressing in. So it's opposite. So very much like one of them was opposite with translations, one of them is also opposite with these compressions and expansions. So there are some similarities. We'll talk about that in class. A couple little tricks that you can use to remember that, but I won't put that into this video. Let's take a look at an example of this. If I have y equals f of 3x, then the a value is 3, which is bigger than 1. So this is a horizontal compression by a factor of 1 over 3, 1/3. So if we had some original graph, and I'll just say, let's just pretend that my original graph was a absolute value graph, then what happens when I try and graph the absolute value of 3x? Well, I know that x has been replaced with 3x, and that 3 is making a horizontal compression by a factor of 1 over a. So instead of this and this, everything has been crunched in, and it looks like this and like this. So all the values have become 1/3 as far in the x direction. And here's an interesting little side bit for you. This graph in green that I just wrote looks very similar to this graph, which is a absolute value graph where you've done expanding horizontally by a factor of 3. So the question is, do you know the difference in these two graphs? Because there is a major one. So we'll explore that in class and see if you can come up with the difference in these graphs. They do look the same, but how they're created is different, and there's an important feature to that.